In this video, we're going to talk about factoring. We will hit solving by factoring, but the main focus is going to be factoring. Okay. First of all, factoring, the term means to separate an expression into its factors, which are the pieces that get multiplied together to obtain the expression. Okay, zero product rule, we'll come back to that. Now, as far as factoring options go, the first thing we want to look for is a GCF, greatest common factor. If that occurs, we need to undistribute that first. Then we do want to check for a couple of special cases. We'll get to that in a minute. Unfoiling, if you remember learning FOIL, first, outer, inner, last. We'll look at that next. And then product sum method will be for the tougher cases where we have a factor in front that is not 1, okay, but we'll get to that in a minute. All right, so for this first one, I'm looking at 4 minus 4p, and I do notice that both of those terms are divisible by 4, so my greatest common factor is 4, okay? I'm going to undistribute that. That's what factoring means. I'm going to pull that to the outside, okay, and then I'm going to look at what does 4 get multiplied in order to obtain each of our original terms. So 4 times 1 is 4, and 4 times p is 4p. So 4 and 1 minus p are the two factors. So this is a factor itself, and the 4 is a factor. Okay, those are our two factors. Factors can have addition and subtraction inside of them, but they'll be grouped together with parentheses like that. Okay, so that's factoring that one. Looking at the next one here, I've got negative 3x cubed and a negative 3x squared. I'm going to look at the constant part first. Obviously, both of those have a negative 3 in them. So negative 3 is going to be part of my GCF. And then also with the x cubed and the x squared, I remember that my exponent tells me how many times the variable is multiplied by itself. So if this is 3x's multiplied, and this one is 2x's multiplied, then I know that x squared, or 2 of the x's, is a factor in both. So that means x squared is a common factor, okay? But then there's one x left over on the first term, okay? And then none left over on the second. Now, 3x squared is this entire term and is also my GCF. That doesn't mean I don't have another term on the inside here. What that means is I'm left with a 1. Okay, because I'm still multiplying it by 1 in order to obtain what I started with. Now, something to be very careful of, since we pulled a negative out, then that means this is addition. Because if we put minus 1 in there, then if we redistribute, we would have plus 3x squared. Okay, and we want minus. All right, so negative 3x squared times the quantity x plus 1 is our final factor to answer there. Okay. All right, so that's GCF stuff, and GCF can be mixed in with other methods, so you still want to look at that first. Now, looking at this next one, I don't have any common factors between these three terms, so what I'm going to do now is I'm going to unfoil, or I'm going to try and go backwards into the two binomials that were multiplied to obtain m squared minus 4m minus 45. Okay, so if you think back to FOIL, the f was the product of the first terms, and that's m squared, so that means we probably have an m and an m in our two first terms there, because m times n, m is m squared. Now, the last terms have a product of negative 45. We have some options here. We could do 1 and negative 45, or negative 45 and 1, or we could do 3 and negative 15, or negative 3 and positive 15. We got a couple of options. So the way that we choose is we ask ourselves, what factor pair of 45 has a sum of negative 4? Okay, has a sum of negative 4. And there's some things that the signs can tell us as well. Because the product is negative, that means I have to have one of each sign. If my product were positive, then that means I would be multiplying either two positives or two negatives. But because my product is negative, I know I have one of each sign. And in this case, it doesn't matter which one goes where, so I just wrote the plus and the minus. Now, I'm looking for a pair of terms that have now a difference of 4, okay? And I know that 9 times 5 is 45. Okay, so one of these is going to be a 9 and one of them is going to be a 5. The way that I pick which is I want them to add up to -4, so that means I need my bigger number to have a negative sign. Okay, so I'm going to put the 9 with the negative and the 5 with the positive. Now it does not matter which of the two factors gets written first. I could write m minus 9 times m plus 5 as long as I don't have m minus 5 and m plus 9. I need to make sure the 5 is positive and the 9 is negative. Okay? Now here we're going to pause for a second and talk about the zero product rule that's mentioned up above. The zero product rule says if the product of two or more factors is 0, then at least one factor must itself equal 0. Okay, so think about that for a minute. If you're multiplying a few different numbers or variables or expressions and you know that the product is 0, is there any way to multiply non-zeros and get 0 as a product? Okay, can we multiply two numbers that aren't 0 themselves and have 0 be the answer? And the answer is no. Okay, so what that means is that, let's say this were an equation to start with. Okay, if this were an equation, now we would use the zero product rule to solve. Remember, solving means find any possible value for the variable that would make the statement true. Okay, so now if these two factors have a product of 0, then that means one of the original factors, either the m plus 5 or the m minus 9, has to be 0 itself. Okay, so what that allows me to do is it allows me to write two small equations, and these then are easy to solve. So m can be -5, okay, or it can be +9. Okay, so that's adding the solving step onto the factoring, and I'm not going to do that for all of these, but if you have an equation instead of an expression, so if it has an equal sign, then after factoring, you set each of your factors equal to 0 and solve the individual factors. Okay? And again, that's only if it's equal to 0. So if it's not equal to 0, you might need to move everything to one side first. Okay. Oh, hold on. Lost my pen. There we go. Okay, looking at this next one, numbers are a little bit bigger here, but because I'm looking for a GCF first, I notice that all three terms are divisible by 5. So the first thing I'm going to do is I'm going to divide all three terms by 5, and I'm going to move that 5 to the outside. Okay, so then I have an n squared. 55 divided by 5 is 11, so minus 11n, and 120 divided by 5. If you watched the last video, I talked about multiplying by 5, and a shortcut for that would be adding a 0 and cutting it in half. Okay? To divide by 5, we do the opposite. We double it, and then we drop the 0 off. And it doesn't matter what order we do that. So I can drop the 0 off of the 120, which is then a 12, and then double it to get 24. Okay? So that's just one option for dividing by 5s mentally. Okay, sorry, I had another interruption. All right, so now what I want to do is I want to see if I can factor this inside. Okay, if I can factor that any further. So keep the 5 here, and I'm going to draw my parentheses and see if I can unfoil that. I know that n times n is going to give me n squared, so I'm going to start with those. And now I need a product of positive 24 with a sum of negative 11. Because my product is positive, the two signs have to be the same. Because the sum is negative, then both signs are negative. So I know that I can put minuses in both of those. Okay? And then again, we go through our factor pairs of 24. Make a list if you need to. 1 and 24, 2 and 12, 3 and 8. We can do this systematically until we get to one that works. 3 plus 8 is 11, so 3 and 8 go in here, okay? And so then it's factored. Now, because this one is not an equation to start with, I'm going to stop here. Don't make the mistake of solving if there's no equation to solve. On the last one, I added an equation to it, but this one was just an expression, okay? All right, this next one has 4 terms. You're not going to see a lot of factoring with 4 terms, but I'm showing you this to show you another method that's going to make the following expressions easier to factor, and that's called factoring by grouping. Okay, so when we factor by grouping, that's usually because we have 4 terms. And what we're doing is we're using GCF factoring but 3 times. Okay, so first I'm going to look at these 2 terms and these 2 terms separately. Okay, on the first 2 terms, I'm looking for the GCF, and I see that 14 and 6 are both divisible by 2. Okay, and then n cubed and n squared are both divisible by n squared. So 2n squared would be my GCF. Okay, when I move that to the outside, I have a 7n plus 3 left over. Okay, and then looking at the next 2 terms, I see that I can take a negative 3 out of both of those. Don't forget that sign right there, negative 3. If you're taking out a positive, then put plus 3, but don't put it right up against this other closing parentheses. Okay, so if I take out a negative 3, I have 7n plus, because I took out the negative, 3 again. Okay, so that's just using the GCF with the first pair and the second pair. But what I notice is that now this and this are the same factor. Okay, I have the same factor in both the beginning and the end here, so I can again use GCF factoring to pull that out. Okay, even though it's got more than one term in it, it's still a factor. So now 7n plus 3 is my common factor. And what am I left with over here? It's multiplied by 2n squared, and here it's multiplied by negative 3. So this is now completely factored. Okay? I would want to check to see if maybe this second one can be factored again, like the difference of squares or something we're going to talk about in a minute. In this case, it can't be, but that is something that you would check for. Okay? So that's factoring by grouping. Now, the reason we talked about factoring by grouping is because whenever we get to trinomials where the leading coefficient is not 1, and it's not one where we can take that 9 out, in this case a 9 out of all 3 terms, then we want to try and use another method for factoring. Now, you may have learned a couple different ways to do this. Maybe you learned a shortcut. If you already have a method that you are comfortable with and you can get to the right answer, then by all means you can use that. What I'm going to show you is a product sum method that works for me and can work for you if you're unsure. Okay? So this is the way it's going to go. Our goal is to figure out how do we separate that middle term into the 2 terms that were added together to get 46R. If you remember, when we FOIL, we multiply first, outsides, insides, last, but the O and the I, we then combine because they're like terms, so this becomes the O plus the I. And we want to go back into its original 2 terms, and then once we have 4 terms, we'll factor by grouping. Okay? So this is the way we're going to do it. We're going to start by finding a new product. Instead of 40 being the product, like on the last ones, we just used the last term. Instead of 40 being the last product, I'm going to take this, I'm going to multiply it by the first term. Okay? So instead of a 40, I'm going to look at that as 9 times 40, which is 360. And it's okay if that number gets a little bit big. Okay? So I'm going to look at 360 as my new product. Okay? So now the question is, what factor pair, let's see, so this is the new product. Okay, so now what factor pair of 360 will add up to 46, which is still my middle term? So I'm doing the same thing that I did on, like, look at the one right above. We said, how do we get a factor pair of 24? One second here. We said, how do we get a factor pair of this that adds up to the middle term, except I've changed the last term. Instead of just using the last term that was there, we multiplied it by the first term. So now it's 360. Okay, that's where that comes from. So our sum, okay, we need a factor pair that adds up to 46. And in this case, that's going to be 10 and 36. Okay, and again, you can make a systematic list if you need to, okay? But I can see pretty quickly that's going to be 10 and 36. So now I'm going to rewrite my expression, but instead of 46R in the middle, I'm going to split that into the 2 terms that were added together to get 46R, which are 10R and 36R, and it does not matter which order you write those, okay? and then I'm going back to my original last term, which is 40. Okay, we only used the 360 to figure out what the two middle terms were, but it's not part of the actual original expression. Okay, now that we have 4 terms, we factor by grouping just like we did on the last one. So looking at these two, the 9 and the 10 don't share anything, but they have an r in common. So we're going to pull the r out, okay? And then we have a 9r plus 10 left. All right, looking over here, 36 and 40. Let's see, I can take a 2 out of both of those, but actually there's a bigger one. I can take 4 out of both. So if I take a 4 out, I have 9r plus 10, which is really convenient because that's what I had on the other one. If these two inside expressions don't match, then you either need to back up because you factored incorrectly, or it can't be factored, okay? They have to be the same, because now I use that as my common factor to pull to the front. And what's left is the r and the 4, so r plus 4 is the second factor. Okay. Let's do another one of those, okay? Another trinomial where we have a different common factor, a different leading coefficient. Now we have a 10. So remember, our first step is to multiply the 6 times 10, make this a 60 for our new temporary product, okay? Now because we have a positive product and a negative sum, then that means they're both going to be negative, so I don't need to worry about subtracting the numbers. They still need to add up to 19. Factor pairs of 60 that will add up to 19 are going to be 4 and 15, and both of them will be negative. Okay, so those are my two middle terms now. So I have 10x squared minus 4x minus 15x plus 60. Okay, again, it doesn't matter if the negative 4 is in front of the negative 15. You do need to make sure you put an x on both of those, though. We need the variable with those because that's part of the middle term. All right, so now we factor by grouping. Looking at the 10x squared minus 4x, both of those share an x and also a 2. So we can pull out a 2x, and we're left with 5x minus 2. Okay, hopping over here, we can take a negative 15 out of both. All right, and we are left with x, x plus 4, that doesn't match. Okay, so this brings us back, and we need to figure out what we did wrong. Oh, I know what I did wrong. Sorry about that. Backing up. Mistakes or avenues to understanding. Can anybody see what I did wrong? I'll give you a second to look at it. Hopefully you figured out it's because I put a 0 on here. Should not have put the 0 on the 6. All right, that's all right. Moving forward. Again, this one was fine. So let's see, 2x, and then we've got 5x minus 2. Okay, now the 15x and the 6, now the only thing they share is a 3. Now I am going to take out a negative 3 because of this sign right here. I want my inside signs to match this. And since the 5x is positive, I need to take out a negative 3 to make the 5x inside here positive. Okay? So if you have a negative in between here, it doesn't really matter what that last one is. We always want to subtract. Okay, so it's going to be negative 3 and then 5x. Now this becomes minus 2 because we divided by a negative 3 when we factored out the negative 3. Okay, now they match and we did it right. So we pull out the 5x minus 2, and we're left with 2x minus 3, and that is factored. Okay, one more of these, and if you haven't been already, it might be a good idea to pause it and try it first and see if you get the right answer. Okay, on this one, hopefully you notice that there's already a common factor between all three terms. Now I can go ahead and factor the way it is using that product sum method, but I want to try and make my numbers a little bit nicer first. And I notice that all of these are divisible by 4. Okay, so I'm going to take a 4 out of everything first. Okay, and I'll have 5v squared minus, now if you're unsure how to quickly divide by 4 mentally, Don't go to the calculator. Try it this way. Cut the number in half. So half of 92 is 46, because half of 90 is 45. And then cut 46 in half again, and that's 23. All right. Mental math is better. All right. And then negative 40, we divide that by 4, we get negative 10. Okay, so I still am going to use the product sum method with this inside, but my numbers are much smaller. Okay. Now don't forget that 4. It stays there. What I'm going to do is I'm just going to kind of draw an arrow and put the 4 down here to make sure to my final answer. But I don't want it really to kind of confuse things in the meantime. All right, so that way I won't forget it, but I don't need it right now. Okay, so looking at this, I need a new product. All right, let's switch. Okay, new product, 5 times 10 is going to be 50. Okay, and then we want a product of negative 50 and a sum of negative 23. So that looks like it's going to be negative 25 and positive 2. Okay, so splitting this, I'm going to move over a little bit here so I don't run out of room. This is now going to be 5v squared minus 25v plus 2v and then minus 10. I'm not going to make the same mistake I did on that last one. Go back to the original last term. Okay, and if you have one negative and one positive, sometimes it's easier to put the negative first, so you don't need to worry about taking a negative out of your second pair, but it doesn't really matter. Okay, so looking at my GCF now, I can take a 5v out, and I'm left with v minus 5. Here, I can take a 2 out, and I'm left with v minus 5. Both of these share v minus 5, so that comes to the front with my 4. And I'm left with 5v plus 2. Okay, so that's a lot of the factoring that you're going to be running into. I do want to hit these special cases first, just because the quicker we are to recognize them, the better, the faster we become with factoring. One of them is the difference of squares. Okay. Or the difference of 2 squares. Okay, and the way to recognize this is there are only 2 terms, like we have on both of these first 2 examples. Both of them are perfect squares. In other words, numbers where we can take the square root and we don't have any radical left, or we don't have any decimal parts or irrational parts. And they have to be subtracted. We have to have one of each side. Okay? Now, the way that this works, I'm going to back up for a second. I'm going to show you what happens when we multiply. Okay, so let's say this is just some generic values. If we have a plus b times a minus b. If we apply FOIL, okay, if we apply our process, we get a squared, okay? And then the outer term is negative ab. The inner term is positive ab. And those cancel each other out. So I really have 0 ab in the middle, which means I don't need to write that. And then my last term, b times negative b, is negative b squared. Okay? So if I were to multiply 2 different binomials, okay, binomial will be these 2 terms in the parentheses like we've been using, where everything was exactly the same except the signs in the middle. Except the signs in the middle. And again, it doesn't matter which one's positive and which one's negative. What will always happen is that the middle term will cancel out and we will be left with this, okay? Which is the first term squared, the second term squared, and subtraction in the middle, okay? And because of that pattern, what we can do is we can very quickly go backwards from the multiplied form to the factored form, okay? If we recognize that we have 2 perfect squares that are being subtracted, we can very quickly jump back to the factored a plus b and a minus b, which is what I want to do here. So let's look at this one, 9x squared minus 25. Because I noticed that these are both perfect squares, and because they're subtraction, then I can take the square root of each of these and jump straight to my final term. I don't need to worry about product of negative 25 that adds up to 0 or anything like that, or looking for a GCF or some other way to factor. But I can say, okay, 9x squared, that's 3x times 3x. And 25 is 5 times 5. Whoops, didn't really leave myself enough room there. There we go. So 5 and 5, and again, always one of each sign. Doesn't matter which one comes first. Okay? So with the difference of two squares, you take the square root of the first term, square root of the second term, and we jump straight to the answer. Okay? This next one still has two terms. It's not the difference of two squares, but I do want to get to that, and I can do that by looking for a GCF first. Okay? In this case, both of them are divisible by 3, so I factor out a 3. And I have a 4n squared minus 9. And now that is the difference of two squares, which is good. So I can factor this a little bit further. The square root of the 4n squared is 2n. Square root of the 9 is 3. And again, one of each sign. Okay? Remember, as we're going through this, if we have questions that ask you to solve, we need to be setting each of those factors equal to 0, but we don't need to worry about that right now. Okay, these last two are both perfect square trinomials. A perfect square trinomial, here's another formula that you're going to want to remember because it makes factoring much easier. Okay, if we were to multiply a binomial by itself, okay, if we're multiplying a binomial by itself, and again, this is a generic case here with a and b, our first terms, our product would be a squared. Our outside and our inside terms would both be ab, which means we have 2ab in the middle. Ran out of room again, 1 second. Okay, and then the last term, b squared. Okay, so this one takes a little bit more, but it's still very much worth memorizing. If you recognize that your first and your last terms are both perfect squares, then you check and see if the roots of those, which would be a and b, multiplied and then doubled, are in the middle. And if they are, you can jump straight to the factored form, which is this over here. Okay? So looking at this example on the left, I could go through the product sum method, but I'm noticing that 25 is a perfect square, 9 is a perfect square. The square root of this is 5, the square root of this is 3. 5 times 3 is 15. When I double that, I do get 30. So this fits the perfect square trinomial pattern. Okay? So I can jump straight to a 5x in both of the first terms, a 3 in both of the last terms, and because that is positive, both of these are positive. Or we could write it like this. Okay? Either of these is an acceptable form of your answer. Don't write both and don't write or. Just pick one and go with it. Okay? This next one, I don't have perfect squares, but again, I notice GCF. All of these are divisible by 5. When I pull the 5 out, I've got 4x squared minus 4x plus 1. And now I see a perfect square and a perfect square, so I'm going to go ahead and try that. I will be checking my middle term. So square root of 4x squared is 2x. Square root of 1 is 1. This is negative, so I'm going to put negatives in both of these. And let's double check. 2x times negative 1 doubled is negative 4x, so that does work. And that is my answer.